of it is curved in such a way that you can see it. And this we proved in the early 1900s, which is kind of fascinating. During a solar eclipse, if I'm not mistaken, is where when we were able to prove it. Um, so gravitational lensing is one way they've been able to prove that this is it. So we see the cause, we just don't know. Like quantum physics, we see it, we just don't know what the fuck it does. So we still
Right.
haven't touched it, we still haven't measured it, we still haven't seen it, we just say it's dark energy because we can't see it, and it's dark matter because we can't see it.
Yeah, I mean the effects are measurable, but as for what it actually is, because we can't see it, we can't,
Doesn't interact with light.
can't actually quantify it. Yeah. So what the hell is it?
So, which brings me to my next thing is if it's 95% that it makes this up, we've traveled in space enough, and maybe we haven't. Maybe that is my egotistical, human-centric way of looking at this. But I
Mhm.
feel like we've traveled enough in space, and we've viewed space enough that because especially dark matter, because it's still matter. Like if you look up the definition of what matter is, let's look it up. Maybe I'm wrong. Definition of matter: physical substance
So
in general, as distinct from mind and spirit in physics, that which occupies space and possesses rest matter, especially as distinct from energy. Um,
yeah.
so it occupies space, but I don't know. It's just weird to me that if we're sending satellites out there like Voyager, like it's not hitting the matter. Like again,
Well, I
maybe I'm
mean,
understanding it wrong, but
so they're still trying to find actual examples. I mean, they have a few candidates of what they, what these scientists think that it could be. Um, one of them called weakly interacting massive particles,
uh-huh.
um, or WIMPs for short. Another one is axions. So these are extremely light particles that have been predicted by particle physics. Sterile neutrinos is another one that they may think that it could be, or primordial black holes, which that was all the rage last year for some reason. They were saying black holes are in your living room and stuff like that.
Yeah,
So
but
yeah.
see, I had that hypothesis a while back. So I had
Hmm.
that hypothesis a while back. Like, I wonder if dark matter is just super fucking tiny black holes where it loses me and where I push back. Again, I'm not a physicist. 100% very amateurish at this shit. Is black holes do interact with light.
Right. They pull it in. Or
It,
they
correct. And with black holes, we do see what is incorrectly called Hawking's radiation. So you see that glow around it because of some radiation expelling from it. So it does interact with light. Dark matter does not interact with light. Dark energy does not interact with light. So I think the black hole hypothesis, from my perspective, ignorant, and I mean that by definition. I just don't have all of the information. From my
mm,
ignorant point of view, is I don't think it could be black holes. Also, what the fuck would make a black hole that tiny? If I forget what the size is, but if you compacted the Earth to the size of, I believe, a marble or something thereabouts, I forget the exact size, it would technically turn
yeah.
into a black hole. The problem with this, the Earth would never become a black hole because it doesn't have enough mass. So
Mm.
there's not enough to compact for it to become the way I understand it.
You imagine the size of the singularity then. Microscopic.
Yeah, it'd be it just I don't know, just that one doesn't make sense. The black holes one. But I did think about that a while back. Is that's the mass. Um,
Yeah. So right now there's tons of underground, these huge detectors that they're just trying to catch one particle interaction of dark matter. Big giant tanks of liquid xenon that are sitting miles underground just waiting for one blip. And
that's how we
so
ended up
far,
with
nothing.
that's how we ended up figuring out gravitational waves, huh?
Yeah.
We ended up
Yeah. And
proving
these things are sizes of like entire cathedrals. I mean, they're not small.
yeah,
Just to detect one invisible particle.
yeah. Will we ever be able to measure it? I think the answer is we already do measure it. We already do measure it. Dark energy, and if dark matter doesn't interact with light, how will we ever see? I don't think we ever will. We don't see neutrinos that go through us, but we can still measure the waves. We can still measure. There's ways to measure shit we can't see. We can't see atoms technically, um,
Mhm.
but we can still measure them. We don't see a lot of the shit that we measure. We don't see. Um,
So
Go ahead.
yeah, I mean, there's some scientists that really just don't even believe that dark matter exists at all. I might be one of those. So that's why, because it confuses the heck out of me. But um, you know, the theory behind that is that gravity itself might be behaving at different scales in our galactic system, and not necessarily that there is an existence of dark matter.
Yeah, yeah, but then you would have to take Einstein's equation into account how fucking perfect it is at those large scales.
Yeah.
And
Um,
dark ma I'm sorry, all of this does take that into account. Now, I did have to pull it up, and I had a query, and my question was, "So Einstein's math is wrong?" And the answer I got, this is I typed this into to the ChatGPT, so take it for what it's worth. I'm not fully trusting it. I'm not fully believing in it. So take it for what it's worth. But kind of just last minute, right before we jumped on, this was the question that I asked, and this is what it spit back out. Again, it's AI, so take it for what it's worth. I don't trust AI 100%. In fact, I trust about 20%. So I haven't rebutted. I haven't said you're wrong. I haven't looked at real sources. I don't even know the math enough to know what the fuck I should be asking. So, short answer, Einstein's math is not considered wrong. What's happening is this is from AI. What's happening is the universe behaves in ways that requires either additional ingredients or deeper physics. Here's the so Einstein's core idea still works extremely well. Einstein's theory of gravity, general relativity, predicts that mass and energy curve space-time. This relationship is expressed in Einstein's field equation, and you guys can look it up. Einstein's field equation. Very roughly, this means how space-time curves, because there's two equations. How space-time's curve, and then the right equation is the matter and energy causing that curvature. So again, look up the Einstein's equation if you guys want to follow this a little bit more. The framework has passed every direct test we've thrown at it, including gravitational lensing, gravitational waves, Mercury's orbit, GPS satellites correction, black hole imaging. So the core math works extremely well. Where the problem appears when we apply Einstein's equation to the entire universe, observations show two big mismatches. Galaxies behave as there's more mass than we see. The expansion of the universe is accelerating. The equation still works, but only if we add extra components. Those components are called dark matter and dark energy. So,
right. Um,
go ahead.
there's another part of that. Have you heard of modified Newtonian dynamics?
No.
It's basically the idea that our equations of gravity might be incomplete.
Yep.
So,
But I think there's evidence of that. I think there's always been
Right.
evidence that are even Einstein's, and we look at this in quantum more than we do in at a large scale, um, is how that math doesn't we're basically back to where we were with
Mhm.
Newtonian physics, where we call it the God's correction,
Right.
where shit didn't make sense. People would just allow that's just God correcting it, just because we didn't understand it. So I do firmly believe that. I don't think there's any scientist that would disagree that we're still not complete on the math for all of this. But the question is why?
The Newton. The Hey, what happened here?
Oh, you're still here.
Okay.
Yeah.
Yeah, the motivation behind it was basically just to explain galaxy rotation curves without invoking dark matter. So it's a very well known theory, though, developed in 1982.
So, but the theory is we just don't get we don't understand the science. We don't understand the math. I'm sorry.
Yeah, it modifies Newton's law of gravity. So which results in modified gravity, and then also modifies Newton's second law, which is modified inertia. But modified
Force,
gravity is the primary.
it's force, or I'm sorry, mass equals force times acceleration. Is that the second one?
Yeah.
Yeah. So
Yeah.
it modifies it how though? Like it adds what to it?
It explains that the gravitational force experienced by a star in the outer regions of the galaxy decays more slowly than predicted by Newton's law of gravity. So now we're invoking decayed matter.
So because we're at the
Mm.
farther edges, our energy or our mass is decaying because it's gravity, so it would be our mass, not our energy. Our
Mhm.
mass is decaying faster than if we were closer to the black hole?
Decays slower.
Slower. So
Yeah.
we would have if there was the same size star as our star closer to the black hole,
Mhm.
the one closer to the black hole is decaying faster than us, than our solar system.
Right. Correct.
And the theory is because it is doing that, it's got less mass. We have more mass. If we started off the same, we have more mass, and therefore I don't know.
Leads to more inertia.
Correct. I get it, except kinetic energy equation would still be at play,
Mhm.
unless I'm wrong about this. But half mass times velocity squared would still mean that we're still traveling fucking fast. We would still leave. So I don't think that that would fully explain why we're still held together, right? Like
Um,
it's that I get it. It does kind of make sense because you're closer to the center of the black hole. So there's this idea that it's kind of tugging you in. So slowly it's pulling some of that mass towards it. I get it. But then we
mhm.
there's been proof that that black hole isn't like a vacuum. It's not sucking things in. But if the moon were closer to us, it would start to separate and we would absorb a lot of it because of gravity. So there's that. Like I get it. I get it. But also it would doesn't explain how we're still here and we didn't get flung out of the Milky Way. That's where I get
Right.
caught.
Yeah,
That
this theory, it basically, it's noted here that it struggles to explain things like gravitational lensing and gravitational
yeah,
waves. So that's one of the weaknesses of this
which is
entire
a pretty big
theory.
fucking weakness. It's a pretty big fucking
Yeah.
weakness. Like, it's not just a tiny one, and maybe that's why nobody regards it as much. I'm sure it's a pretty famous theory that nobody even bothers to pay attention to anymore. Now, dark
Right.
energy is the opposite. Dark energy
Mhm.
is the reason why the universe is expanding so fast. Like
Right.
it's fast how it's expanding. It makes no sense. The math doesn't math when we're talking about how fast it is expanding. This one was the one that was discovered later, right? Like this one was the one that was discovered in the late 80s, early 90s.
Correct.
Who discovered this
I'm
one? Do you
looking
know?
this up now. I do not offhand. Let me see
Use the Google. Use the Google machine.
that one. Yeah. I mean, it still says 68% of the universe. They call it anti-gravity. Uh,
Anti-gravity.
Come on.
Doesn't say who discovered it.
It does not.
Huh. Let me see if I can
But
find
it'll tell me the difference from dark matter. It says dark matter. While dark matter has gravity and pulls matter together, dark energy acts as a repulsive force, pushing space apart. So they
Dark
represent
energy
two
was
distinct.
discovered in 1998. Holy shit, a lot later than I thought it was. In
Ah,
1998 by two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter and the High Z Supernova Search Team led by Brian Schmidt and Adam Rees. So these were the
see.
humans. Saul Perlmutter, Brian Schmidt, and Adam Rees were the physicists that discovered it. They ended up winning a Nobel Prize in 2011 for the findings. The
Wonderful.
methodology that they use, the team used, and this is just Google. I'm not looking at anything official, just a simple Google. The teams used type IA supernovae as standard candles to measure distances to far off galaxies and determine the expansion rate of the universe over time. The expected result was that gravity from the matter would slow the expansion of the universe. Instead, they discovered an unknown repulsive force, dark energy, driving acceleration. The impact, this discovery fundamentally changed cosmology, revealing that dark energy makes up roughly 70% of the universe.
Right.
Bonkers.
Yep. So right now, yes, it's around 72% dark energy, dark matter sitting at around 23%. And then atoms, which is actually what we can see at that minute scale, is at about 4.6%.
Fucking crazy. Now, these guys were looking up into the sky and they were saying, we want to see how fast they're separating, but because they have mass, they should be moving pretty slow away from each other. We know this from our own um, understanding of our own solar system that the sun and the earth is slowly separating. I can't remember the exact number. I think it's or the even the moon is every year is a quarter of an inch further than the previous year, if I'm not mistaken. Somebody should
Hmm.
check that shit out. But I think it's a quarter of an inch further away this year than it was last year. So we know that from our own solar system that we're slowly moving apart from one another. We're slowly moving apart from one another. A lot of it has to do with our orbits. Our orbits are just but the reason our moon doesn't leave, the reason Earth doesn't leave the solar system, Pluto, all that stuff is gravity. It's plain old gravity. So they were looking up into the stars, the way I understand it. They say these galaxies should be moving at this rate if they do the math. What they found out is it's actually moving a fuck ton faster than what it should be
Hmm.
separating from one another. So this is where they discover the effects of shit we don't see, called it dark energy. Called it dark energy. That's
Correct.
that's basically the gist of it.
So basically, most of our reality consists of something that barely interacts with us at all. Doesn't even care about us, doesn't know our names,
That's
nothing.
weird. That's weird. Well, and
Yeah.
and one of the weird things about this is that these two energies are doing oh, 1.5 inches, a lot more than I thought. I thought it was just a quarter of an inch. An inch and a half every year. The moon
Mm,
is moving away from the Earth. An inch and a half. That's pretty substantial.
yeah.
Um, yeah, I mean that's because in 12 years, that's a whole fucking. I don't know if you know how to do math, but that's a little over a foot every 12 years. That's fucking crazy.
It's
But anyways,
18 inches.
18 inches, that's fucking crazy.
Yeah.
That's bonkers. So, at any rate, we have dark matter, which is holding galaxies together, and then we have
Mhm,
dark energy that are separating galaxies completely apart. Now, I
right.
did study this. I did look it up. Now, I don't know the math, and I don't know the equation, but I did find out that in the galaxy, dark matter is the superior force because obviously we're being held together, and dark energy is obviously the superior force everywhere else outside
Mhm.
of the galaxies. So like
Yeah.
they don't necessarily battle each other. They're just working in completely different areas. Um, I guess you can argue. One could argue um, that the dark energy, because it's pushing up against the galaxies, is kind of helping us stay together as well.
Yeah, it could be pushing us, closer to center. I mean, that's not the way it's working, but yeah, that it could also be if it's to form some type of a force field around our galaxy, it could be what's also holding the galaxy together.
Together. I don't know if that's true. I don't know if it's been proven. I don't know if there's already a science, but it makes sense.
Nobody's yeah. Nobody's looking at that right now. I'll tell you that.
But it would make sense. I wonder if it's that. You heard it here first, maybe. I wonder if it's just dark energy that
Let's go
is
apply for your Nobel.
it's it's pushing the dark energy is pushing so much and we're so together in our masses. It's basically like if I pushed you or pushed your kid closer to you, um, you as a father would tug in. Again, this is just a stupid analogy, but like if I push your kid towards you, I'm dark energy, I push it towards you.
Hmm.
Because you've got that mass, you're obviously going to tug it closer together. Um,
Yep.
anyways, like I don't know if that's true. Probably not.
Not in my case. If it's my son, he's bigger than me now, so I don't know.
But in terms of the universe, I mean that kind of makes sense, but I don't know. I've got nothing else. I like my brain is already like I don't know.
All right,
Super
so you can see why this is the worst subject for me. I hate this
but
one
but
because
it's so weird that you say that because they've all been like this. They've all been shit that we know exists, but we can't explain, which is a lot
right.
of physics, by
Yeah.
the way, and it's a lot of life. Is we see the effects and we see the causes of it, but we just don't know why. Um,
Right.
so this is no different.
So, I mean, just to wrap it up. I mean, our brains can see atoms. That's it. Everything else. Oh, and we can see light, but neither one of those are dark matter or dark energy. So we
And
can't see any of that.
we know that for sure.
Yeah.
Yeah.
It doesn't interact with light and it doesn't interact with any atoms.
So it doesn't
It
interact with
may
atoms.
be, well, it's pushing or pulling atoms, or pulling mass either away or towards it, depending on if it's your theory or everyone else's. But
But then it is
um,
interacting with atoms then.
it interacts with atoms. It just doesn't really interact
With
with
light.
us. I don't know. It's not interacting with any observable instruments that we have.
Yeah, okay, yeah, like, it's not it hasn't as far as we know, it hasn't pushed the Voyager off to the
Right.
side. Um, as far as we know, the Voyager's not moving faster once it left the it technically hasn't I mean, super technical, it hasn't left our solar system. It's on the outer edges of our
Mhm.
solar system. But even then, you'll have people that don't agree on where our solar system ends. Um,
They don't agree on where our atmosphere ends, so, I
yeah,
mean,
that one's bonkers. I forget who I told. It might have been Isaac that I told that our atmosphere, depending on who you ask, technically is far beyond the moon. That the
right.
moon is still technically in our atmosphere, and a lot of scientists agree on that. There's not a 100% consensus on it, but um, many scientists do
There's
agree.
there's fewer scientists that will also tell you that all of the planets also are in our atmosphere.
Yeah,
So, and that would be our entire galaxy, but yeah, they're saying
that's
that
not
our
the case.
galaxy is,
In
yeah,
our
that's our
atmosphere?
entire atmosphere. Yeah,
They're full of shit. They should take away
really.
their
And it
take away their
and they're
computer.
saying that if it's not in our atmosphere, then we wouldn't be able to see them with telescopes and things like that. So that's, I don't know how you
Yeah, but
can
then that'd be
say that.
beyond our galaxy. That would be way beyond our galaxy. Like, the Andromeda Galaxy is way beyond our galaxy, and we can see the Andromeda Galaxy.
It's true.
Like,
But
every galaxy that's out there that we're now seeing with the James Webb, I mean, we can see and they're not in our so their argument now is that basically the entire universe is in our atmosphere.
correct.
No. No, if it was the other way around,
if if that's the case, can't we breathe in space? I mean, we're
no
not
shit.
doing that. So
Yeah,
yeah,
but we can't even breathe in Everest, so I can see that. Like, we need help
uh,
to breathe in Everest, so I can kinda see that just because oxygen is a lot more limited, up there
right.
just because of reasons. That's another thing we should talk about. How Everest is not the tallest mountain. Um, yeah, batshit crazy. Creepy stuff. Invisible stuff is creepy. Yep, it is. It is. Physics. This whole universe is weird.
Right.
Entire
So
universe.
now we've talked about ghosts and dark matter, both things that we're not supposed to be able to see.
Yeah, but one's real. The other one's not. One is real. The other one is not. I'll believe dark
Right.
matter. We need to explore ghosts, but um, they're not real. Ghosts are not real. I'm still
Uh,
terrified of them, but they're not
you
real.
are?
Yeah,
It's just a
it's
change
weird.
in frequency. That's all it is.
It's
It's a
weird. I worked at
change in
really
energy
old
states.
yeah, when I was a CNA, I worked at what used to be an old plantation house, as a CNA. They converted it into a nursing home.
Mhm.
Um, super old, late 1800s, early 1900s. Um, one of the oldest houses here in the state of Colorado, and it's fucking massive, massive, and you'd have to go do laundry down in the basement,
Oh,
and
yeah.
yeah, so everybody tells you it's haunted, and of course, I never seen anything, but it's such an old house, so you turn on the heater or whatever, science does science things, it's shit starts to pop and expand and contract and, creaks,
Oh.
it's definitely creepy for sure, but, um, anyway, ghosts are not real. They're not real.
Yeah, one of the office that I'm working on right now is in downtown Denver, and it's creepy. It's about 4 floors,
Yeah.
and yeah, I've been walking all through that area, and there's certain parts that I'm just like, "Nah, I don't know about this place."
Correct. Correct. Yeah. Um, neutrinos are very ghostly for sure. For sure. At any rate, I think that's about as much as we can get out of this conversation. Um,
Yep.
Yeah, that was a fun one. It's an interesting one. Um, and just so we're another example on how very little we know about our universe, and
Mhm.
how weird and almost kind of perfect it all ends up working out. Um, yeah, yeah. One of the topics that I want
Yeah.
to talk about, maybe we talk about it next podcast. Maybe we'll see. Is this idea of um, that us existing is not as rare as we think it is. That
Okay.
it's almost inevitable that we were going to exist. Not so much that it's a miracle that we exist, but according to math, it's pretty inevitable that our existence was it was a matter of time. So we should probably explore that. But anyways, if you have nothing else to say, I probably have
No,
nothing else to say. I appreciate you guys. Thanks for tuning in. Thanks for the comments. Super duper appreciate the comments. Um, yeah, there's nothing else other than 5% is us and shit that we find interesting and important. The rest of it is nothing. Absolutely
no.
nothing.
Well, it's not nothing.
Oh, fair,
it's
fair, fair.
it's something. We just don't know what it
We
is.
just don't know what it is. More proof that we're super insignificant. Super
Right.
insignificant. So, at any rate, I appreciate you guys. Thanks for tuning in. Please share this, like it, subscribe to Richard, subscribe to my channel, all that shit. We'll see you next week.